Moving right along. In this section, we're going to look at data with some examples and try to get into this data-driven style of thinking. So this picture is my favorite scene from the Ron Howard film, Apollo 13. We have a NASA engineer who walks into the room with a load full of stuff, and he says, listen, we got to make this fit into the hole for this using nothing but that. And then my favorite line in the movie, and perhaps in all of film, is voice number 3 that says, all right, we better get some coffee brewing, somebody. I want to emphasize here that data analytics is a creative process. Engineers love linear thinking, but when we get this pile, like a pile of data, and we need to make sense of it, that is the time for creativity, and nothing other than creativity works. So rule number 1 in existing building data analytics is that you're never going to have perfect data. You're never going to have all the data that you want. The data that you have will always be flawed. You're always going to wish that you had a sensor or a meter that was 5 feet away from where it actually is. That will always be the case. But we have to use what we have. We have to use the data that we've got. So let's start to chunk through some of these. The first data set we always have is the monthly utility bill. There's 2 things that we can do with monthly utility bills. First, we can check for a relationship. When we download utility data, we also get cooling degree days and heating degree days for the months. Now, it is very common to find no relationships. In other words, the stated conclusion would be something like the monthly electrical use has no relationship to the monthly cooling degree days, or the monthly natural gas use has no relationship to the monthly heating degree days. The first time I saw that, my head exploded because it stands against everything I've ever learned as a mechanical engineer. But I will tell you, it's very common. In this example that I'm showing on the screen, there is a relationship. So we're looking at a linear regression of the relationship between heating degree days and monthly natural gas use. The relationship here is reasonably strong. We have an R-squared that's better than 80%, and we have a line that actually has a slope. So the y-intercept of that line tells us how much reheat is being used in the non-heating months or in the summertime. You can actually divide that number by 730 hours a month and the building size. And in this case, you'll see there's an average of 24 BTU per hour per square foot every hour of reheat or baseline heating energy. It's a pretty big number. And then the slope of the line tells us how strongly this building responds to cold weather, the strength of that correlation. And in this case, every heating degree day in the month adds 0.02 BTU per square foot. We can take this further. When we do a heating load calculation, there's 2 components. There's an envelope component, we call that UA delta T, and then there's a ventilation component, we call that 1.08 CFM delta T. If we combine those, we can kind of get a single scalar factor that's related to delta T. So it would be a UA plus 1.08 CFM all multiplied by delta T. So what we can do is look at the dates of the meter readings for a few months and then merge the natural gas bill data with the weather data from those days. You use a heating temperature of 70 or 68. In this case, I'm using 70, and you literally solve for K. The units are BTU per hour per degree less than 70. And in this case, K is about 20 BTU per hour per degree below 70 in natural gas. This is actually the exact same thing as a heating load calculation, but we're using real data instead of design weather data and design data about our envelope. And I've showed this example for heating because it's a little simpler. We can do this for cooling. It's just a little more complicated because you have to assume an hourly electrical use that's not related to cooling, but it's the same process. Another source of data that we pretty much always have is the 15-minute interval data from the utility, and that gives us a bunch of opportunities. The easiest way to really dive into that data is a free tool by PNNL, and it's called ECAM, Energy Charting and Metrics, a name only an engineer could love. If you've never seen that tool, check it out. It's an Excel spreadsheet. It's 100% free, and on the website they have about an hour and a half worth of training videos that are pretty good. And so you can immediately start to get some charts like this, and those values can connect to our design assumptions. For myself, I always like to take these numbers and divide by square footage because our load calculations assumptions are usually in watts per square foot, right? Like lighting and plug loads, etc. We talk about those in per square foot. Another source of data that we have are the diagnostics. Hopefully many of you know that we have an enterprise fault detection and diagnostic system that's called Clockworks. So for buildings that are connected to Clockworks, we start with that diagnostics page. Clockworks is an amazing tool. It runs diagnostic tests every day, every week, every month, and then it produces this list of faults. And they're sorted. There are comfort faults, there are energy faults, and there are maintenance faults. So you can just download this list and take a look at a month or 2 months worth of fault data from the building, and that'll show you exactly where the problems are in the building. It'll show you which zones, which valves, which coils, and which pieces of equipment are having problems and what problems they are having. Amazingly valuable data. If we're not connected to Clockworks, then we can still get a list of faults. You have to get it from the BAS system. Every BAS system since the inception of BAS system has a list of alarms in it. So these are the alarms that our engineers get every day. So simply gathering a couple weeks or a month's worth of these alarms lists will give us an inventory of where those problems are happening. At KP, unfortunately, we don't have a single system to track these BASs. And we also don't have an enterprise single system up and running to track maintenance work orders and tasks and track deployments to different things. We are working on that, but right now that's not up and running. So let's get into zone diagnostics, assuming you found some data. What do you do with it for design purposes? There's a list of diagnostics that's down the left side of this slide here. And then these are some diagnostics on zones. The first histogram on this slide is the unoccupied test. I call this the 4 a.m., 4 p.m. tests. So you look at what the zones are doing at 4 o'clock in the morning versus what the zones are doing at 4 o'clock in the afternoon. They should be different. And in this case, their behavior is different, so that's a good thing. And the second histogram that you see on this slide shows the damper and valve position during occupied hours. This particular zone spends a lot of time at 75 to 90 CFM, and then it spends another big cluster of time at 135 to 150 CFM. But notice that the heating valve, the average heating valve position is pretty much always 70% or 80%. Well, that's problematic. Why are we heating? Pretty much across the whole range, the whole spectrum of this zone, why are we doing heating? This is an overcooling and reheating problem. For fan systems, the list of diagnostics that you see on this slide are pretty much the same. So again, we'll want to do the 4 a.m. and 4 p.m. test. In this graphic, you can see that that's happening quite well for this air handler. Every air handler that we have should be at a reduced state at 4 o'clock in the morning. That's frequently not the case in our hospitals, but that's something we want to note during design. And then we also want to look at the actual fan speed, right? This fan speed never gets above 75% in this slide, and it spends a huge block of time down at 25% fan speed. One thing that we can do is we can take a variable like fan speed or fan capacity and plot it against outside air temperature. That's what you see in this smaller picture. We have outside air temperature on the x-axis and then that fan speed on the y-axis. So notice how the data is not a bell curve. It's not normally distributed. It's a multi-nodal distribution. We have a big node at 25%, which means regardless of temperature, whether it's 50 degrees outside or 90 degrees outside, we're spending a lot of time at 25% fan speed. Then we have this second weaker node up around 40%. And then we have these even weaker nodes above that, a weak node up at like 50 or 60%, and another very weak node up at 75%. Another thing to note here is that the highest number, the highest demand for fan power, does not occur at the hottest temperature. Again, as a design guy, the first time I saw this, my head exploded because I would have expected that the biggest number you ever see on this chart lines up with the 90 or 95 degree temperatures. But pretty much everywhere we've looked, that's usually not the case. That's also with heating systems. The peak capacity rarely, if ever, occurs in the coldest hours of the year. This is another air handler historical graphic. This one's a little prettier because it has rainbows. But another useful way to look at that data is to round the outside air temperature into 5-degree bins. So each one of these rainbow stacks shows the distribution of CFMs in a 5-degree bin. So that black color at the top of the rainbow represents the top 1% of points within that temperature bin. And then the purple bar is the top 10% of data for that temperature bin. The green bands in the middle go between 40 and 60% within that temperature bin. Again, you can see in this one that the peak, 11,500 CFM, occurs in the 85-degree band and not in the 100-degree band. And of course, I would be remiss if I didn't tell you that this air handler is a 23,000 CFM air handler. So the peak we've ever seen in it is 11,500 CFM, slightly less than half of what it's designed for. Another diagnostic that designers should always be interested for is the variance around any controlled point, a controlled temperature or a controlled pressure. We could look at this for any controlled point, supply air temperature, pressure, water temperature, etc. In this case, we're looking at air handler supply air temperature control. And just to let you know, the ranges that we find are often not normally distributed, like this one is not a normal distribution, and they're also not symmetrical, and they're not centered on the center point that we would expect them to be centered on. In this case, we're looking at variance, and so we would very much like for that variance to be centered on 0, but it's not. It's centered on about 5 degrees below that. And so that's actually not uncommon. Here are some of the checks that we would be looking at on a hydraulic system. The list is very, very similar, right? And again, we frequently see for poor temperature control in the hydronic systems. The graphic on this page is a pretty typical example, plus 10 degrees, minus 12 degrees. Anytime we look at an existing system, we face a choice as designers. Are we going to keep this or are we going to change this? If this variation in supply water control is acceptable, then we would base our new design around a system that has that much variation in it. If this variation in water temperature is not acceptable, then we need to deliberately do something to change it. And this chart is talking about variance, but this comes in play particularly when we talk about delta T. When we find a poor delta T, we must either accept that and have our new design respond to the delta T that we actually found, or we must change it. And changing delta T can be very difficult. Delta T can never be solved at the equipment in the cup. It's only a function of what's happening in the zones and the valves of the system. We can also look at historical system capacity. This graphic here shows the historical capacity of a heating system, a boiler system, again, versus those outside air temperature conditions in 5-degree bins. So notice again that odd phenomena that the highest heating load occurs not in the 20-degree bin, but in the 25-degree bin. Again, defying the laws of physics there. And in the case of boiler systems, I have to point out how big the variance is between traditional calculation methods and reality. On this project, the design engineer did a load calculation in the classic manner, envelope and then outside air, and they came up with 2.5 million BTU. And you can see the maximum load that we've ever incurred in this system is 500,000 BTU. So that classic load calculation is off by a big factor, a factor of 5, right? Finally, this is a bit of a teaser. We can also look at historical loads in zones. We're going to talk about this in about 10 minutes. So we'll just tease the topic right now. What you're looking at here are the historical loads in about 17 operating rooms. And I really want you to learn the word historical loads today. So as a recap of this section, data analytics and data-driven design requires creativity. You're never going to have perfect data. You're not going to have the data that you want. You're not going to have the meter in the right location. And so we have to use creativity to take the data that we have and shore up some foundations of our design based on that. This, by the way, was the longest section that we're going to see today. So please remember to type in any questions that you have into the chat on this pretty big topic, using data and doing assessment.
Where can we get the historical data from eBuilder?
Where can we get historical data from eBuilder? Well, okay, so I'm hearing that question two ways. So the first one is, if you're talking about the historical load data, then we've got that published out on a public video. It's actually a YouTube video that's going to be part of this California decarbonization project, and so that'll be public and widely available for historical loads. I think, though, that this question may refer to, hey, I'm just starting a project in a building. How am I going to get a hold of that utility data or the interval data on the utilities or the data that's coming from the building automation system on that building, a year's worth of data? And so that's going to come from my team. And what we're starting to do is, as we get into the OPR phase, we know that a project is coming at a building. The project manager is writing an OPR, and so we'll go and pull down that utility data, request that interval data, and just drop that data up into the folder of eBuilder, so that by the time you come along to do your design, it's sort of sitting there waiting for you. Ideally, that's sort of how it would happen. If it's not, then you would simply ask. I have an engineer assigned to every project. And so we'd always be able to dig in, and it's pretty quick. We can assemble data pretty quickly for these projects.
What would be the procedure if no historical data available? Do we rely on the loads calculations only?
Well, first off, what we're talking about here is the playbook for existing buildings. And if it is an existing building that Kaiser owns, there is no scenario where there's no data available. So if nothing else, we have the monthly utility data, and we can get that going back 10 years. That is actually a really big deal, just to take a look at the monthly utility load data and sort of compare that. You can take that and divide by the operating hours and see whether or not your calculations are within an order of magnitude or inside of range or outside of range. So I would actually kind of reject the question. I don't think we have any scenario where there is no available data on an existing building. The fact that a building exists in this day and age means that it left a paper trail, and so we can get data on that. I don't think there are any utilities that we deal with where we can't get interval data at some form either. We can't always get natural gas interval data, but we can pretty much always, and I'm trying to think of an exception, I don't know of one, we can always get 15-minute electrical utility interval data. So if you have monthly bills, now you know where your building is using on a month-to-month basis. You can get utility data that tells you what you're doing at midnight and 4 a.m. versus 4 p.m. You can then correlate that to the weather. So if you're looking at a building and you're saying, hey, there's no data here, then, there is. You just got to go find it, get it.
Is this intent that all future retrofit projects, including energy engineering services, data analytics, and retro commissioning services from the mechanical consultant? Some firms have different individuals that specialize in these tasks.
So yes, I guess I'm trying to devise the question there. This is kind of going to be our design program playbook. So throughout this, I've told what our design program requirements are, and that'll be so within the design phase, these requirements are there. And so I think where the questioner was going was that there are, some firms have energy modeling specialists. Some firms use generalists to perform energy modeling. Some firms have commissioning folks on staff that can go out and do some field assessments and look at BAS data during design. Some firms don't have that. And so those are absolutely the questions that we're frankly talking to people about during interviews. We want to look at the capabilities and the resources that the firms have to get engaged in that type of work or in this type of work. And so, and that's shaking out differently within the marketplace right now. There's some firms that are, we know design firms that have data analytics departments, right, where they have people that are doing Python data analytics, as an internal design department within the firm, same way you would have CAD in the old days or something like that. And so I can't really answer what an ideal, well, I can, you can call me personally and we can talk about firm composition. I'll tell you what I've seen in the marketplace and where I have some opinions about where I think that are going, but. We'll state them here.
Is there a proposed mechanism to obtain zone level issues in a building? Would we expect facility engineering support the design engineer to identify these issues?
Yeah, so there's three levels to that. If we have our Clockworks, our fault detection and diagnostic system installed, then we'll be able to see that live. We'll be able to see real data in the diagnostics. So the zones that are acting out will have faults associated to them, and so you'll be able to see those. And similarly, the zones that do not have faults, it is reasonable to assume that they're not acting out and they're not out of whack. If we don't have that diagnostic system involved, then the next level would be the BAS itself, and looking for alarms within the BAS, zones that are out of temperature or zones that are, over temperature. That's where we would look phase 2. And then the sort of lowest form of data, obviously, is expert opinion, but that's where you would ask for that. So an interview with the facility engineer to say, what are the zones that, what are the 5 zones in this building that are out of whack or causing you problems? They definitely know where those zones are. And if you walk into a building where they don't have any trending capabilities, for example, then that's when you might initiate trends on the zones that are indicated to gather some data to use in the assessment.
Can you shed some light on why mechanical design load more than 3 times of the total energy usage?
Yeah, I assume you're talking about the boiler system, and that's something that we've seen now. I think it's been a theme of the last 10 years or so, where we've just seen that kind of over and over and over again. That particularly the heating side. When I was a design engineer, I got out of college with Chris Miller. They taught us that we used to do it by hand almost, or in a spreadsheet. You would take the envelope of the building, multiply that by the coldest possible temperature you thought that it would see, and then you'd take the outside air and multiply it by the coldest temperature. You would include no association for any internal loads, no association for any building massing, and just say, okay, that's how we size the system. That's extremely conservative, and we all know that that's extremely conservative. And so as we look at our buildings, the loads are just way less than that. I wish I could say that's the whole problem, because we've also seen in energy modeling that you get a fairly sophisticated energy model in there that's supposed to account for mass and the time that the building was unoccupied and things like that. And we still see those heating loads just sort of fundamentally overestimated or underestimated, or just off. And so that's been something that we've, I wish I could account for what the huge variance is in there. I can't always.
Our next question is from Chris Miller. Would you want submeters on a building in addition to get granularity?
Not necessarily. That's going to be something that happens essentially project by project. So some of the examples, I can razz on Chris. Chris and I actually went to college together. So, but some of the examples I know that we've chatted about are, so on a new project, when we're doing boiler systems, natural gas boiler systems, it is necessary to put a natural gas meter into that system in order to validate the efficiency of the system. So you literally, and a BTU meter in the downstream. You literally can't tell if your system is 80% efficient without those 2 meters. And so the acceptance criteria themselves often dictate a minimum amount of metering that's necessary for the validation. But beyond that, my view on submetering is a little tainted because I come from the owner side and the capital side. And I always remember talking to a guy at a Southern California Edison, actually, who told us that the budget for metering of any energy savings should be less than 5% of the savings that you're planning to meter. And so from that perspective, Very often the schemes that we talk about to get into really granular sub-metering things are just too expensive to actually provide a whole ton of value. And so I always try to start it at that perspective, which is frustrating because that turns me into the owners that says, no way do I want to spend on those meters. But we have to bear that in mind.
Is there a process in place to verify or confirm data quality from the BAS per BMS systems for future projects to benefit the data analytics process?
The short answer is no. That is a great question. I think for anyone who's not catching where I think you're going with that, and I don't know who Michael is, but obviously the data that we're getting, even when we have a building where we have every point in the building connected to an enterprise diagnostic system, and so we have thousands of points worth of data coming at us, there's always the problem of what is the actual accuracy of those sensors? What's the drift in those sensors? One of the things that we've seen is that you can have 5 units on the roof, each of which has an outside air sensor, and you could just simply look at those outside air sensors relative to each other, and you'll find there's a 4-degree spread among the different sensors that are ostensibly reading exactly the same thing. No, we don't really have a process in place for, how are we going to manage that or correct for that or make good decisions in that light on a long-term basis. I don't think we really have a game plan. So that falls back into the nature of creativity, right? We're going to have to look at the data that we have, understanding that it will always be imperfect, and try to make reasonable decisions based on what we've got coming at us.
Benchmarks be released by KP for consultants to use?
So to take that one by one, first off, Clockworks. I think Clockworks has some standard training protocols that they've posted. I thought there was a web series. I may be mistaken on that, but some of the basic user interfaces. If not, that's something we can absolutely do. How to get into Clockworks once you have a password. What are the basic modules of Clockworks, and how would a design engineer click on? That's actually a great suggestion. I think we could do that immediately if it doesn't already exist. So I'll follow up on that. Some of the other things, like the utility data always comes at us in a very similar spreadsheet form. And so that linear regression that we do there, that's pretty standard. We already have 30 of those spreadsheets. And so I think we'll give those out. I don't know that we're going to post that kind of tool on the InfoZone per se, but I think we'll always be, I think within my team, we're always willing to share any tools that we have that are in Excel or anything else. And we're willing to share any tools that we steal from the design consultants that do work for us, or that we pay for the design consultants that do work for us, and share those. So please do ask. We probably have whatever calculation you're thinking of starting. And if you're just looking at a blank Excel spreadsheet, with cell A1 and you don't know what to do, yeah, please ask. We've probably seen that calc before, and we can show it to you.
What are some good resources to get familiar with how to these different types of data analysis?
That's a great question. We've actually, in my team, what we did, and I've talked to some consulting engineers that have talked about this too. In my team, one of our engineers found a set of YouTube videos that just went through some examples on how to do it in Microsoft. In Microsoft, there's 2 tools within Excel, and then also another tool called Power BI. There's this Power Query Editor, which is a very powerful data analytics tool. And so I think every member of our team did this, literally just like a 2 or 3 hour training off of YouTube, which is amazingly eye-opening. If you haven't learned about Power BI, or Power Query, then I would highly recommend. That'll change your life today. You could do that training starting now, and by 5 p.m. you'll have a different perspective on the world. There are some other tools out there that some of our consultants are getting into using, Python scripts and some other data analytics tools. That actually varies from firm to firm. what tools we see them solidifying on and standardizing on, and you know, like anything else in consulting, there's going to be preferences around that software. Yeah.
What would be a good way to verify existing zone level issues?
Existing zone level issues. I'm not sure I understand that. I think what we've been doing is the first thing to do, just to sort of summarize the playbook, is to look at any diagnostics that you have. If you're connected to a diagnostic systems and you know which zones are alarming cold or alarming hot, that's a great first indicator. Or you can look at the list of alarms that's showing up on our building operator's screen every morning, look at a month's worth of that and see which zones are warm, which zones are hot. Then we would get into the assessments of basically the overcooling assessment, the undercooling assessment, and the 4 a.m., 4 p.m. Type of assessment. The most common thing that we run into is overcooling and reheat. The way that you see that is that you see a CFM delivered to the zone, and you see a heating valve that's sort of constantly open, or the average valve position above 30% indicates that you're probably overcooling that zone and reheating it. On the other side of the coin, you could have a zone that's failing to meet temperature a certain fraction of the time, and it's always at maximum condition. That's the undercooling condition.